Right. Really, it's with great pleasure that that we at Pervasive Technology Institute host Bob Hanisch here at Indiana University Bloomington. Bob has been a kind of a major voice in the open science space for quite a few years now, and someone that when I am thinking about the future of open science, I make sure I consult. So I was just like quite honored, Bob, that you had time to visit us. Bob is actually an astronomer by training. I believe, yeah, you all, Scott is aware of that, our other astronomer now in IT, and is, and in his, in his more astronomy focused role, he was the first chair of the IVOA, the International Virtual Observatory Alliance, the executive committee of IVOA, and this was in the 2002-2003 timeframe. He has been involved as one of the leading voices in the Research Data Alliance, is currently serving on the council of that. And in his role, his state role he's been in for since 2014. He is in the he's the director of the Office of Data and Informatics, which is in the Material Measurement Laboratory of NIST, but in general has been a spokesperson for issues of data management for the agency. In the role he's in, he's working on data management and analysis practices. He has pushed efforts in material science data, the representation of material science data, and recently told me this morning at breakfast that they are working on adopting one of the RDA recommendations on persistent IDs for instruments and adapting that and adapting that within NIST for instruments within NIST, within the Material Measurement Laboratory, which I think is a good statement both for RDA and for NIST being at the leading edge. NIST, as if I may just talk to the to NIST activity, NIST is playing a key role in CHIPS Act funding, and we were talking about the data from things like fabrication that NIST may end up managing and the proprietary nature of it. So he's very hotly involved in some very current relevant topics right now, which he'll be telling us about. So again, Bob, with great pleasure. Bob and I have known each other for quite some time. So again, thank you, and I'll turn things over to you.
Well, it's a delight to be here. I think it was at least a decade more ago. My last visit to Bloomington. I'm still disoriented. The campus is so huge. It's a good thing that Beth was driving. I don't know where we are. But before I go on, thank you very much, Beth, for the invitation to the nice introduction. Let me just say a brief word about NIST. NIST is National Institute of Standards and Technology. We're part of the Department of Commerce. Commerce has 12 different bureaus. Is this okay?
Yeah, I think you need to.
Is that any better?
No, maybe under.
Yes.
I can hear it great. How about here? Is that any? It's upside down. Yeah, it is. There we go. Okay. Perfect. All right. Testing 1, 2, 3. All right. Yeah. So NIST is an organization with about 5,000 employees altogether. Government employees are about 3,000. The remainder are contractors and guest researchers, and of course administrative staff. Our main campus is in Gaithersburg, Maryland. We have a major satellite campus in Boulder, Colorado. You may know about the atomic clocks that NIST operates. They're based in Boulder. And one of the accomplishments of NIST being the National Metrology Institute of the United States, metrology being the science of measurement, is that we measure things very, very carefully, very, very precisely. We now measure time to 1 part in 10 to the 18th, which is 1 second in the age of the universe. And we can tell the difference between clocks running at a tabletop to the floor because of general relativistic time dilation. That's how accurately we can measure things. So it's a pretty cool place to work. We do research in many different areas of science and engineering. We watch cement dry to understand its tensile characteristics under different conditions. We characterize the properties of steels and other materials for use in building. We do fundamental research in material science, biology, chemistry, a lot of work in computer science, in particular computer security. NIST actually sets the federal standards for cybersecurity. In other areas, the standards work is work that we do with the community as a consensus builder. We will act as a neutral convener of organizations to build consensus standards. So that's generally what we're about. The Material Measurement Laboratory, where my office is based, is about 1,000 people altogether, focusing on materials science, chemistry, and biology. And my group is right now around 20 people, federal employees and contractors, supporting data management needs, not just for MML, but really quite broadly for all of the NIST research staff. So today I'm going to talk about some of our data management activities, our public data repository, our standard reference data, how we do data discovery using infrastructure called resource registries. I'll talk about data acquisition and our work on laboratory information management systems, and then spend some time on our research data framework, which describes the data lifecycle. And Beth is one of the wonderful members of our advisory board for the RDAP project. A word about data that cannot be open. Beth alluded to the CHIPS activity, the Semiconductor Revitalization Act that Congress passed last year, and a few other things that I hope are of interest to you all. But I'll start with this. 2023 is the year of open science. This was a resolution started actually by NASA late last year, but then endorsed by the Office of Science and Technology Policy, OSTP, declaring 2023 the year of open science. This means that some 13 federal agencies have agreed to participate in activities that foster and advertise the roles that they play in promulgating open science practices. And NIST is one of them, I'm proud to say. Our activity largely focuses on the data that we make available to the public through a public data repository. And our public affairs people have a LinkedIn presence, and this was just posted last week. We love sharing data. We are making 100 terabytes of data available electronically for over 900 projects in our public data repository. So this has gone from basically a dead stop before I came to NIST 9 years ago to where we now have researchers very actively sharing not just their publications, but also the data that support those publications. And, this has just been almost revolutionary. 10 years ago, this was rarely done in most fields. Astronomy was sort of at the leading edge of this, in that we took data public very early in the process. But other fields have been much more, shall we say, patient, if not even reluctant. But astronomy is lucky because, as our former collaborator Jim Gray from Microsoft Research used to say, astronomy data is worthless. There's no commercial value to astronomy data, so it's easily shared, easily exploited by others. That's not true in chemistry, or it's not true in material science, where there are many commercial interests involved, and not all data can necessarily be public. But that said, our public data repository, which is available at the URL data.nist.gov, is where we are collecting all of the research outputs associated with peer-reviewed publications. Although we also allow for things called data publications. So even if you don't have a journal paper, you can simply document the data set and publish that through our public data repository. We have an internal review process, both for papers and for data. Every group at NIST has basically a data steward or data sponsor who's responsible for reviewing the content, especially the metadata. Is this data set sufficiently documented that it can be used by others? So things that are published here have a certain quality. They are research data, a little bit different than our standard reference data, which I'll talk about in a little bit. And we have made it hopefully easy for people to discover information by having these major groupings around information technology, manufacturing, chemistry, and so forth. So if you want to drill down into a certain domain, you can do that quite easily. As an example, I just put in a search for titanium alloys, and anything that in the metadata has something to do with titanium or alloys shows up, and the resulting field 24 data sets are found here. You can click through to read about the data set in more detail. And all of this metadata is automatically populated into a landing page so that when a researcher is ready to make a data collection available, they go into an internal facing site called MIDAS, which stands for Management of Institutional Data Assets. They enter some basic metadata about their data collection, and then this landing page is automatically generated for them. They also have a tool where they can edit the metadata, update it as need be. And then a link is generated to where you actually find the data. So here's a link, like NIST alloy data. So if I were to follow that, I get to a website that is hosted by our Thermodynamics Research Center in Boulder, Colorado, which allows further search according to the components in the alloy. So this data does not actually reside in the public data repository, but is linked from the metadata collection of the public data repository. Other data does reside in the repository itself. Here's an example of some additive manufacturing data around another alloy. And here the actual data sets are resident in the repository, which physically resides in the Amazon cloud. The software for the repository, the data themselves reside in the Amazon cloud. And for all of the data in our cloud-based collection, we store a so-called gold copy. So the data is served up from the working copy, but in case there's any corruption, any problem with the data, we can always go back to a gold copy, which is checked like on a daily basis for its integrity. So we have a way here of assuring that these data are not inadvertently or even advertently corrupted, and that consumers are getting the real thing, which is pretty important for us at NIST. We are very much about high quality. One of the silver linings of pandemic is that people couldn't get into their labs. So they couldn't get into their labs, and they had a lot of data that they had not written up for publication. And so you see, starting in April of 2020, which was the start of lockdown in the Washington, D.C. area, the rate of publication of data sets really started to skyrocket. And so on the right here, we have the volume of data, and on the left, the orange line is the number of data sets. So over 20,000 or 25,000 data sets and 250 terabytes of data in the public data repository, and having grown from, with a factor of more than an order of magnitude over that time period. Standard reference data is a bit of a different beast. NIST has been in the business of providing standard reference data since the late 1960s, when Congress passed the Standard Reference Data Act, and it asked NIST through the Department of Commerce to provide the highest quality, highest vetted data possible in domains that were really essential for US commercial interests. So if you want to know how much steel to put into a bridge and what kind of steel, if you want to know the expansion coefficient of some material that's going to be running through a pressurized pipeline, you come to the NIST SRD collection and you can retrieve that information. Our staff scientists, who are domain experts, review that data meticulously, and as a result, the Standard Reference Data Act allows NIST to copyright this data. That's very unusual for government-sponsored research data, but it's because we have to protect the integrity of that data. We can't have another organization take it, modify it, claim that it's NIST SRD, and then we find that actually they've changed things in ways that we do not agree with. We also charge for some of these data. When I first came to NIST, coming from astronomy, where all data is free and open, I thought, what do you mean we charge for data? Well, the rationale is that these data, for example, go into our mass spectroscopy reference database, is loaded into the vendor supplied equipment of every mass spectrometer made around the world. As a result, the consumers of those instruments have embedded in it this reference database that's value added. So it's good for the economy, if you will, that we have this mechanism that allows us to continue to update the database with time and improve its scope and the quality of the content. So of the 80 or so SRD databases that we have available, 10 or 12 are sold or licensed. The rest are openly available for free. We also are manage a public source code repository. So I consider computer source code sort of a special class of data. It's it has different characteristics, and it has to be executable, and has to run with certain dependencies and so forth, but it's still information. It's still assorted data. And our researchers have generated over 600 public repositories on GitHub. These are all now indexed using common metadata schema. And through this source code repository at code.nist.gov, you can see what's available, again, by type of content, and you can get links to any associated data sets and publications. We borrowed the interface for this from Lawrence Berkeley Lab and just sort of customized it a bit for our use at NIST. But you can find here, as I said, over 600 public repos. So,
I'm sorry,
yeah.
Bob, get back a slide. Do those repos, is there a curation to get a repo into this collection?
there is not. Basically, it's a researcher decision. Do I want to share my code? We encourage sharing of code. But there's no real review process for the software. And it carries a license. If people have taken the care to put the license in the README file, that basically says this code is provided as is with no warranty, et cetera, et cetera, et cetera.
Is it archived, like, is it an archived version, or is it in a living repo?
It's in a living repo. So about data discovery, I assume here everybody knows about the FAIR principles: findable, accessible, interoperable, reusable. Findability is the starting point. If you can't find data, you obviously can't reuse it, because if you can't access it, you can't reuse it. So findability is the start. And when I was working in the astronomy community, the first thing that we developed there in the context of the virtual observatory was a set of tools that allow you to find data. And finding that data requires knowing what resources are out there. You put metadata about those resources into a registry, which is basically a collection of metadata. So we brought that idea from astronomy into other areas that we have at NIST, in particular in materials science. We built the Materials Resource Registry, the metadata standard for which was developed in the context of the Research Data Alliance and the working group on materials science. And the links are here. And this slide deck, by the way, is available to you if you want to follow the links and so forth at your leisure. You can do that. So what we've done here is collect information about data sources, about organizations, about websites, about documentation, anything to do with material science. And all the metadata is loaded into a standard schema that is customized for data discovery in material science using the language of material science. For example, you can't really see it here, but under type, type of data set or organization is here. But if you go down further on this page, it'll be type of material, type of processing. And there's about a 250 term vocabulary that was developed, a hierarchical vocabulary to describe materials science research outputs. And that is now an RDA recommendation. As Beth and I were discussing at breakfast today, we're hoping that in the future, RDA will actually go a step further and go through a process to make these really standards that can be adopted with all of the imprimatur that comes with using a formal standard. But each of these discovery interfaces is now customized for the particular research domain. So we built a data discovery registry for greenhouse gases. We have a program in greenhouse gas studies at NIST, but it's not just NIST data. Some NIST data is here, but most of the content comes from organizations outside of NIST. One of the challenges there, talking about opportunity is discovery possibility. One of the challenges is ongoing curation, because these sources change with time, things are added, things are removed. And so once you stand up a registry like this, there is kind of an obligation to make sure that the content stays current. That can be a burden, and some things get out of date if you don't have resources to keep them going. But I think finding something is better than finding nothing. And hopefully we'll find the resources to keep them very up to date. We have another one for forensics. It's a very active research program at NIST. And here again, we're collecting metadata about data sets, some of which reside at NIST and many of which do not. We also have one now for science and technology educational materials called Nestor. And you'll recognize a certain similarity in how these look, because they're all based on a common software platform called the configurable data curation system. But here's an example of sort of the metadata that is different, obviously, for STEM resources than it is for materials. So here you have instructional level, school subject, teaching time, educational standards. So all these metadata labels are optimized for the particular research domain. See you later, Devin. And the underlying software is this configurable data curation system, CDCS. This was developed in partnership with collaborators in our information technology laboratory. This is also open source software. Its repository is in our GitHub repository. And it has now been adopted for these resource registries that I just showed you, but also it's in use by a number of external organizations for organizing metadata and data from in various research domains. We are also using this in a new project to encode calibration reports and certificates of analysis. This is more in the metrology area, where there's a standard XML schema. That XML schema is loaded into the CDCS, auto-generates a user interface that allows you to populate the content, modify the content. And it also has APIs that can auto-generate, autofill all that content if it's available in other forms.
Just if I may, just to clarify, this is something that NIST developed, the CDCS.
Right.
Okay.
Right. Not in my group, but we've had strong influence over its development. So let me turn now to data acquisition, laboratory information management systems, or LIMS. LIMS is a software platform that helps you capture and organize data from scientific equipment, to preserve, recover that data, track the origin of the data, automate conversion of data from one format to another, link information systems and work areas, and provide a query mechanism for prior experiments. What we found is there's no one out-of-the-box solution for LIMS. There are a number of commercial LIMS, but they're really designed for things like pharmaceuticals, biotech companies, where they're basically documenting a procedure that happens over and over and over again. In our LIMS situation, we're dealing with researchers who are very creative and doing things differently every day. But still, we want to routinely collect the data, in this case, in our first use case, from electron microscopes in an organized, consistent way with a consistent metadata model that allows people to achieve what I call transportability of data in space and time. So that your successive generations of grad students or postdocs don't have to redo all the experiments that the previous generation did because there was no metadata collected, there was no, you didn't know what they were doing. Across space and time, so to other researchers, so the data can be repurposed. I'll show you an example of repurposing data in machine learning context, but also here, the data are born fair. So you don't burden researchers with having to go back and metadata tag their data because one, if they do it at all, they'll do it poorly. And for two, they usually won't do it at all. And so what you end up with, well, here are the electron microscopes that have been integrated into our, it's called Nexus Slims. So these 4, 7, 9 on-campus systems and 6 in our campus in Boulder. So these are now integrated into our LIMS platform. All of them, the researcher goes to the microscope, logs in, says start. All of the data that they take is automatically captured. All the metadata is captured. The only thing they have to do is basically type in, why are they doing this experiment? That's the only thing that the instrument doesn't know about, right? So that information is added, and then all of that becomes searchable in a centralized database. This is what it looked like not long ago. This is the data collection strategy that we had, right? Drawers full of disk drives, thumb drives. Some, if you're lucky, they were labeled with the date the experiment was run on. Otherwise, good luck. So that is not transportability across space and time. Well, across space, I guess, but certainly not time. So Nexus Slims is our LIMS platform for electron microscopy, and it's this platform that automatically captures and tags information about user experiments without additional user inputs. It's built using some software called HyperSpy. One of the challenges in this area and many others is that instrument vendors make their data available only in proprietary formats. So you have to go through a reverse engineering process to extract the essential metadata that you need to properly annotate that information. So we have written some of those using HyperSpy. Other organizations are writing metadata extractors for other types of instruments. We're trying to collect those together into a library so that people don't have to reinvent these extractors. Yes, sir.
Yeah, I'm wondering, you mentioned these proprietary data formats that come from instrument vendors. It's necessary to do what you said, which is to reverse engineer and extract those data. Do you think this has a potential role in preventing that reverse engineering process in the first place?
I do. In fact, it was several years ago, I said, when we buy equipment, why don't we insist in the procurement that the data have to be available in an open format and with documentation for the metadata? And people laughed at me. They said, NIST is too small to have any influence at that scale on the private sector. But as I'll mention later, working through an OSTP subcommittee on open science, I've been pushing the same thing. And I say if NIST and DOE and DOD and NOAA all said in their procurements, we will not buy your equipment unless you provide data in an open format with documented metadata, we're not going to buy your stuff. So I think that's the leverage.
That's a good lever, but I think the other side of it though is sometimes there may only be one vendor for some of these instruments, effectively. Yeah, I mean, in electron microscopy, there are at least half a dozen. I don't know some of the other fields quite as well, but they might be a single vendor lock-in. But I think it's the sort of thing where if you get Zeiss and you get JOEL and a few others to join, I think the pressure will be on the other vendors to participate. That's my hope.
Just a quick extension of that question. So you're part of the Department of Commerce. Can the Department of Commerce can drive some of these standardization in the instrument market? I mean, so when you say, we won't buy, it is only just for your use. But if the Department of Commerce says that it should be for the national consumer, then I think it can be broadly applied. I think there is any
Well,
Department
that-
of Commerce-based influence on this.
Yeah, no. So Department of Commerce is a kind of a funny government agency because there are really two scientific bureaus within Commerce. NOAA, the National Oceanographic and Atmospheric Administration, and NIST. The rest of it is largely statistical. Of course, census is part of Commerce, several business-related bureaus. So our scientific clout is pretty much limited to NIST and NOAA. But that's where if we partner with DOE and DOD, and NIH invests heavily in microscope equipment and so forth. I think we would have the clout necessary to make that happen. I'm also in the process of trying through the Board on Research Data and Information of the National Academies to have them convene a roundtable comprising vendor representatives, academic representatives, and government representatives to address this issue of interoperability of data from commercial instrumentation. So that hasn't happened yet, but I think if we have the power of convening of the national academies, that would also go a long way toward influencing these commercial sector vendors. That's my hope. This is the architecture of our electron microscopy limbs. I won't go into too much detail here, except to say, we collect the data from our instruments on the left, extract their metadata. These instruments reside on a dedicated network called the Research Equipment Network, because a lot of the computer controllers of these instruments are running Windows 7 or right, things that are not up to security standards, so they're firewalled off. But then we have very controlled pipes through the firewall to extract the data into the common central file server. And it's integrated with calendaring systems, with electronic laboratory notebooks, with information about the actual physical samples, with the standard metadata schema as well. And then integrated in a way such that.
So I'm sorry, Bob, if I keep it back. So does that imply that people are using the instruments remotely, or that there's a back end to a more persistent store, which is
There's a back end to a more persistent store, which is a central file server here. Each system has a local store, but we automatically, through the limbs at the end of a session, migrate the data taken in that session to the central store, capturing its metadata along the way. That metadata is embedded in the schema, which is encapsulated in the CDCS.
So yeah, okay, so thank you for that. That's what's evident here. So is the access remote, or is the access physical and on-site?
So the access, once it's into the central file store, can be done from anywhere on our network.
I'm sorry, I mean the person that's using the
Oh,
instrument.
so right now, most of the access is, there's a physical person who goes into a room and signs into that computer.
Yeah, that was not. Okay.
Another thing that we are putting into acquisition requirements going forward is remote control of instruments. We don't want to have a $7 million microscope in Boulder that someone in Gaithersburg can't use because they're not in Boulder. So remote control. There are some issues about that. These electron microscopes operate at very high voltage with very high vacuum. So probably you need some operator physically in the space to make sure that the procedures are done safely. But there's no reason that the scientific control can't be done.
Somebody has to mount the sample.
Somebody has to mount the sample. Somebody has to make sure that the vacuum pumps are running properly. It's, but
Thank you.
so just as an example of the virtue of collecting all this information, one of our researchers, 643 is just a code for their organization, used tens of thousands of these electron microscope images that we collected, 22,000 files here, to automatically identify which ones were diffraction images and which ones were something else. So it's just a very, very beginning of the potential of discovery. Once you have aggregated all this data with a common metadata schema, to be able to do performance or to do experiments on it that you could not do in a single experiment, single observation. So I think this is going to be an area in the future where we see a lot more articulation, a lot more expansion of our scientific outputs as a result of being able to look at data in the aggregate, not in the specific for individual observation. And this is very new to people in material science and biology and chemistry. And astronomy is kind of the norm. And I was impressed the other day. I saw some of the latest imaging from the James Webb Space Telescope. The thing being observed was Neptune. And you see the planet, you see its rings and everything, but you see hundreds of galaxies in the same frame. So an observation intended to do X can do Y and Z as well. It may not be quite so obvious in material science, but once you have 50,000 microscope images to look at, and you can auto classify them saying, this is this kind of material. This kind of material has the following macroscopic properties. You start to open up the discovery space beyond the level of any single kind of experiment. And this is just the data growth in the electron microscopy system. So it's been also quite dramatic once people have gotten back on campus. Let me talk a little bit about the research data framework. This is a project that we started at NIST a little over 3 years ago to answer the question of who are the players, what are the issues surrounding research data management in the long term. And we, through a series of workshops where we engaged the community very broadly, came up with a concept that has 6 major life cycles in the research data framework lifetime: envisioning, planning, generating and acquiring, processing and analyzing, sharing, using, reusing, and preserving and discarding. And what we've tried to do here, or why are we doing this? To make a map of the research data space, provide a guide for stakeholders in research data management to help them understand best practices and how to plan properly to provide open science and open data, but also understand how much it costs to do this efficiently. What are the risks, in particular the risks of not doing this, and to build a consensus document that takes into account all of the inputs and conversations we have with stakeholders in the research data area. And so we want to help people answer questions about, how long do we keep data? How do we assess data quality? And how do we measure the value of research data? And this is where I would say again, Beth has been a wonderful member of our advisory committee as we've gone forward here. There are many stakeholders in the research data environment, from government agencies and national labs to universities such as this, data providers, national and international organizations like RDA and CODATA, funders, standards bodies, private sector, researchers, and the public. So there are a lot of stakeholders. We're trying to increase research integrity, reduce costs and maximize efficiency, and ultimately increase scientific discovery and innovation through adherence to the FAIR principles. And this is happening at an exponential rate. Universities in particular are struggling with this. We just are fortunate to have engaged State University of New York, and there are 31 campuses and 2 medical schools who want to work with us to now turn our research data framework into, or to add to it, a how to use guide. How can you use this system, this set of documentation to figure out the best way to invest in your research data management infrastructure with maximum output? So we published version 1 of this framework in 2021. We're now in version 1.5, which will be out any day now. That will be followed by a request for comment that is published in the Federal Register so that we have the widest possible public feedback. And we'll take those inputs and generate a version 2, which we intend to release by the fall of this year. These again are the life cycle stages. Each life cycle stage has a set of topics and subtopics, which are all fully defined in the version 1.5 of the framework. So for example, your VP for research, your provost, your deans, your president, people involved in sort of campus-wide IT would be involved in this envision stage of data governance, whether legal and regulatory compliance issues, what's the data culture and the reward structure? Do your faculty get recognized for data sharing, or is it only a count of their peer-reviewed publications? We want to change that, right, to show that there's real value, intellectual pursuit in data sharing. So each one of these, the planning stage, I won't read through all of them here, but has a set of topics and subtopics. Altogether, we have about 300 subtopics. We have over 600 references that are all linked to the appropriate topic and subtopic. So that what we're providing at this point is basically a road atlas. Shows you all the players and all the constituents. What it doesn't yet do is give you a map, a route from one place to the next. That's what we're hope to be doing with our collaborators at SUNY. But the analogy that came up to me the other day is that we have the atlas. The usage guide will be the triptych. I don't know how many of you used to get triptychs from AAA. If you're under 40, you probably don't know what I'm talking about. But you could go to AAA and say, I'm going to make a road trip from New York to Los Angeles. They would custom print a map booklet for you that had the best places to stay and the best restaurants and everything and the gas stations. And that would, so this is pre-Google Maps or anything like that, right? So the guide to using the RDAP will be the triptych, if you will, for how to navigate through the space. So anyway, there are all these life cycle stages, all their topics and subtopics, preserve and discard. How do you make decisions about keeping data? Who pays for it? What happens when data are abandoned? How do you mark data that it's end of life? It's been de-accessed or it's gone. And then the RDAP also includes this concept of profiles. Based on who you are, what do you need to be aware of? What do you need to know about? For example, a senior executive would be primarily interested in areas around the envision, around data governance, around data culture, around resource allocation. A publisher, like a scientific publisher, a research publisher, would probably be interested in areas around sharing, using, and reusing data. So for each of these topics and subtopics, we have come up with a relevancy score to around a dozen different roles and responsibilities in the research data ecosystem. So you can see yourself in here. We also make it possible for people to customize those profiles if the responsibilities in the organization differ. So the road ahead, version 1.5 release is imminent. We'll do this public comment period. Hope to have a plenary workshop in the summer and then release version 2 in the fall. And then we'll go into kind of a maintenance phase and a phase where we help other organizations to adopt the framework and improve their research data management posture.
Is there a sizable change between 1.4 and 1.5? I was going to share this with someone. Should I wait for 1.5?
Wait for 1.5.
Wait for 1.5.
For example, in 1.0, we did not have definitions for each of the topics and subtopics. So we found that the Digital Research Alliance of Canada used version 1.0 for a self-assessment of their research data management capacity throughout government. We didn't know they were doing this, but we had a feedback session with them afterwards, and they said, well, some of the topics and subtopics were too terse. They didn't know quite exactly what we meant by them. So now each one has a full definition linked to fundamental references. So this has been an encyclopedic work. It's really been required the patience of Joe to get it all put together. But I think it's going to be an incredibly valuable piece of information.
So it went from 1.0 to 1.5. I see, yeah, that helped with that kind of stuff. Okay. And then to 2.0.
Down to 2.0. So let me aim to wrap up here with a couple other short comments. Data and chips. CHIPS stands for Creating Helpful Incentives to Produce Semiconductors. So the CHIPS and Science Act was signed into law in August last year. It is $50 billion to invigorate the U.S. semiconductor industry. So it's a pretty big deal. NIST, NSF, and Department of Energy have major roles. There are a lot of public-private partnerships called CRADAs, Cooperative Research and Development Agreements. And I say some data will be private or restricted. In fact, probably most data will be private or restricted. Who do we want to see this data? We want US manufacturers to see this data. Do we want Chinese manufacturers to see? No, I don't think so. So we have to be very careful about how we transmit this data. We do have some cases at NIST where we have restricted public access. Our forensics databases, for example, mainly we want to know who's using them and for what purpose. It's public data, but we ask you to sign a usage agreement before you have access. But for this, more is needed. We're going to need encryption, integrity validation. We have IT security experts at NIST, of course, but it's really important to establish trust and also to make sure that these data go just into the hands to which they are intended. We want to be consistent with FAIR. FAIR does not mean open. FAIR does not mean public. It means as open as possible, but as restricted as necessary. So the FAIR benefits still pertain, even if the data are themselves restricted in some way, in a major way. Do I see a question emerging or just doesn't?
No, I was gonna make some. I'm trying not to make a comment about blockchain.
You can make a comment about blockchain.
It wouldn't necessarily be a positive one, but anyway.
Now, we have thought about whether blockchain is a technology that would be appropriate here to track who touches the data and make sure that it is traceable back to our origins. Don't know yet. I'd love to get some sage advice on that topic. So this is a big deal. Also, we've been told by the Department of Commerce that any money that we invest in infrastructure supporting chips research cannot be used to support improvements in our computing and data management infrastructure generally. So it has to be walled off, and the wall has to ensure this level of restricted access. So I've been involved in planning activities for the past 4 or 5 months now. I'm trying to figure out ways to do this. But they put us in a very tight box. Like if you need a higher bandwidth network interface to move data from this instrument to this storage platform, now they're saying, well, you can't transfer any other data over that network interface except chips data, which seems kind of crazy. But those are the rules.
So, I mean, is that, it seems excessive, so, yeah, so,
It is excessive.
okay.
It is.
So are there special networks, network technologies where we can, encrypt, while the transfer is happening in these general networks?
Yeah.
Where you can map it with some kind of code that other people cannot see it while they are using the same.
I'm not a network expert, although we do have people who are experts in network technology. Software configured networks may be an answer to this, where traffic that's chips related it maybe runs on the same physical infrastructure, but it's segmented off into a private stream that only chips engaged receivers can connect to. I have to throw in this thing about units of measurement. One of the hats that I wear is the chair of a CODATA task group called Digital Representation of Units of Measurement, or DRUM. And one of the fundamental challenges for interoperability and making data fair is having units attached to the measured values and having units attached that are machine readable. You would think after hundreds of years in this business, that would be a done deal, but it's not. It's not. The CODATA drum has actually cataloged nearly 50 different units representation systems that are in use around the world, of which probably 6 or 8 are the dominant ones. They are not currently interoperable. We are building tools to make them interoperable. But this paper that came out last year in Nature, Stop Squandering Data, Make Units of Measurement Machine Readable, was a call for action from the CODATA Drum and another group constituted under the International Bureau of Weights and Measures, so-called expert group on the digital SI, where we are trying to bring to light the importance of having interoperable machine readable units of measurement in order to not have mistakes like were made here between NASA and ESA that caused this Mars climate orbiter to have the wrong orbit and crash into Mars rather than going to orbit. And I think the last thing I'll talk about is this concept for a US Open Research Commons. This is an editorial that came out last summer in Science, playing catch up and building an open research commons. As efforts advance around the globe, the US falls behind. This alphabet soup is a compendium of national and international efforts to build open science commons, open science clouds, research commons, European Open Science Cloud, Chinese Science and Technology Cloud, Africa Open Science Platform, Malaysian Open Science Platform, and so forth. And the US is nowhere here. We have no national program at this point in time. So I was one of the instigators of this workshop that led to this paper in Science, and working in the context of the OSDP subcommittee on open science. I'm now co-chairing a subgroup on open science infrastructure. And in that context, we are trying to, again, make the case for why US government agencies should come together and co-fund, cooperate some entity that allows for greater interoperability and greater coordination of our investments in research infrastructure resources, be they through federal funding, be they at federal research centers, whatever. This is going to be a heavy lift. There are 27 different agencies who participate in the OSDP subcommittee on open science. Our funding streams in the US government tend to be very siloed between different federal agencies, but EOSC faced the same issue in Europe with 27 different countries, and still they found ways to marshal resources and collaborate. Then again, EOSC spent 500 million euros to get to where they are today. So the US has not invested anything like that in building a common or shared infrastructure. Nevertheless, I think this is the way forward. I think if the US doesn't do this, it's going to be, we'll continue to build silos, and we'll continue to not utilize and not gain all the research benefits we could by making those systems more interoperable. People who've worked in HPC, high performance computing, moving a code from one system to another can be next to impossible. Even knowing what's available to you as a researcher can be next to impossible because there's no integrated place to find what funding opportunity or what resource opportunities are available. So we're trying to start there. And the recently released report of the NARE, the National AI Research Resource, which Beth also had a role in, I think provides a quite interesting blueprint for how we might move forward, though I would replace AI with research in general, and then I think we'd be a long way toward reaching that goal.
That is $2.6 billion price tag on it.
Yeah, it does. Yeah. Well, a lot of that is for hardware and hardware upgrades. And I don't think we need to refund that or fund it again. I think what we need is the part of NARE that focuses on the coordination and integration. And that's a much smaller amount of money.
Does EOSC, if I may ask another question, does EOSC tap into resources where they exist? So if a university or an institute wants to plug in, they can plug in the managed assets.
Absolutely. In fact, EOSC is, as Baron Monso says, EOSC is not European, it's not open, it's not science, it's not a cloud. But it does depend on member contributions in terms of existing resources. There is funding for integrating activities, but each member of EOSC is expected to come to the table, making their compute and data management resources available.
So in your estimation, has EOSC been worth that 500 million investment? Because I think that's the big question. I'm familiar with EOSC and AOSP. And I think every member who is a person in EOSC would have a different definition of what EOSC is, right?
Yeah.
So it's a name that's well known, but I am not sure exactly what EOSC is in the end, because any person you ask has a different message. So there was a huge price tag and they invested in it, but as far as you approach it, it seems to be a name, but not necessarily a set of tangible services that could be.
So two answers to that. One is a very highly placed individual in EOSC said to me, we spent 500 million euros. And I'll say, we're not done yet. He actually said it a bit more tersely or crudely than that, but I don't want to get in trouble since this is being recorded. But the other thing is, I like to think of this as sort of the ratchet effect. This is the thing that we used in the virtual observatory in astronomy, where we would say to US funders, hey, look what the UK just did. They just put 10 million pounds into this project. Look what the EU just did. They just put 8 million euros into this. Oh, well, we better get in the game too, right? So I will point to all of these, whether they're huge successes or not, and say, we need to be in the game. And we're not. So I think that some of these had more success than others. EOSC, I think, is at the tipping point where either will be a huge success or will just say, well, that was a great idea, but didn't quite materialize. But they put a lot of money into this.
The one that stands out, ARDC, I think, has had some success.
Yeah.
The Australian.
And the Canadian one, the Digital Research Alliance of Canada, is brand new. It's a merger of 3 different programs that were separately managed in Canada. I think these are early, but I think the US has to step up. And so there's an organization called OSCAR, the Open Science Commons Executive Roundtable. And I am there as an observer. Senior representatives from these other projects there are there as formal representatives, but hopefully by being as an observer and using this ratchet effect, I can go back like through the subcommittee open science and say, hey, we've got to get our act together. We've got to get some policy in place to be able to.
And there's a lot to learn from the groups that have gone through it.
Well, and the same conversation with EOSC senior leadership, I said, please tell us what not to do. What mistakes did you make so that we don't have to make it ourselves?
Do you have that feedback?
We do. I'll tell you offline.
This too, if I may, this is the statement here, the plain catch-up statement is now, it's hard to tell, 6 months old. It's fairly recent, but have you gotten any feedback on it since it's been published?
There hasn't been a lot. I'll tell you, it was a lot easier to publish that other paper in Nature than in Science. And then Science put this behind a paywall.
Oh, no. Okay.
So that might be one reason that it's not, but that's not holding me back from continuing to advocate for this. And the fact that we have a subgroup under OSTP focusing on open science infrastructure, which we're doing in collaboration, by the way, with Helios, the Higher Education Leadership Initiative on Open Science that came out of the roundtable on aligning incentives for open science of national academies.
So that has 90 university members now. They have a subgroup on open science infrastructure that we are working with on a regular basis to make sure that whatever we do in the government is something that benefits academia. We don't want to invent solutions that academia then says, well, why didn't you ask us? That's not what we wanted.
Good. Yeah, I'm actually trying to get Helios on the radar of our provost.
Yeah.
We do have, thank you. We do have a question here before.
Oh, sure.
Yeah, so. It's on now, but what do you?
Somebody online is asking which data could be queried by CDCS API.
So any of the metadata and data linked from the CDCS metadata is queryable. We expose whatever metadata schema is embedded in CDCS is part of what can be formed in a query, either through its own user interface or through its API. And as I said, these registries have all been built with CDCS as well as other data management tools. We have a registry for samples, for example, that's been built with CDCS, and a number of outside NIST applications have been built with it. So it automatically builds a web query interface, but also auto-generates an API. So it's all accessible that way.
Just and same person. And could it be applied to domains other than material science?
Absolutely. It was built with material science in mind. It was first called the materials data curator, but we now see applications in many different areas. The ones I tried to show here in forensics and STEM education, for example, greenhouse gases. There's one in progress now at NIST on circular economy, monitoring plastics and how they evolve and get into the ocean, things like that. So it is totally domain agnostic, and you come up with an XML schema. It also can work with JSON, although XML is its native language, but it can also import and export schemas in JSON. So it's really flexible.
So
I will just put up some acknowledgements of some of the key staff working with me and the Office of Data Informatics and other collaborators. Sponsorship, and thank you, Beth, and your colleagues here for having me come today. It's been so far a delight, and I look forward to the rest of the day's activities.
Well, I have a question. So you mentioned this Nexus Slims.
Mhm.
Is it tied to one particular instrument, I mean, the electron microscope, or is it a generic framework where, is it easy to adopt for other instruments, other setups?
It's currently for electron microscopes, but for electron microscopes of different manufacturers. So we have developed a simple but common schema for describing electron microscope data that is now used across those different vendor platforms. But it is our intention to put up new instances of Nexus Slims for different types of instrumentation. We haven't started that yet, but that's the next sort of growth path for our plan, is to X-ray diffraction instruments or mass spec instruments or whatever we want to. We'll build a schema that is specific to those types of instruments, and then deploy against the network of those into the Slims platform. Our really grand plan is to build what we're calling basically a nervous system. Imagine that every instrument on your campus was connected in to its own limbs, depending on instrument, and all of those were connected into a central system where you could say, well, who's observing this today? Who's doing that experiment today? You say, oh,
they're doing an experiment on a very similar material to what I'm doing over here. Maybe these researchers could talk to each other. Maybe these data sets could be brought together. So it's the central nervous system concept, and it's one that it's nascent, but I think just opens up tremendous possibilities for applications in machine learning and AI. How could you integrate all these data streams to see things that you don't see through individual observation and computer simulation?
The other question is, building on the online question. So you mentioned that you can, you talked about these registries that are essentially open to beyond material science. And of course, we are building some materials related data together, and we are building our own registries at this point. And so the question is, I mean, if I were to use a registry, I mean, how do I? Is there a process I need to request some kind of a place for this kind of data to go into a particular registry? I mean, are you in the business of hosting people's registries, or is it?
Yeah, so one thing I didn't, the materials registry actually has two functioning instances right now, one at NIST and one that is hosted by University of Chicago and Argonne National Laboratory. They use the same schema and they copy each other's records to stay in sync with each other using a protocol called OAI-PNH, the Open Archives Initiative for Metadata Harvesting, Protocol for Metadata Harvesting. So that's what we would suggest for an organization that has many of its own resources related to material science. Put up an instance of the materials registry, and then we set up the harvesting mechanisms so that you get our records, we get your records, and they're all searchable from each other's interface. We did this in astronomy, in the virtual observatory. We had like a dozen registries all interoperating and all feeding each other. And that way you had no single point of failure, and you were guaranteed to have the most up-to-date information because each organization took responsibility for keeping its content registry up to date. And you just ping them every day or every week, got their latest records. So that's the way to build a federated, integrated system from independently operated registries.
All right.
Wait, are there any, sorry, it's all the same thing. Are there any large scale biological or health related databases?
Sure.
At NIST, is that?
At NIST, not so much. There is the Protein Data Bank, PDB, which was actually started at NIST, but then moved to Rutgers. There's the NIH, of course, is the place where most of the health-related, biologically related databases reside. GenBank, so forth. So, so there are many, and the biological sciences have been really quite on the forefront of this, collecting genetic data for a long time now. Other fields that I'm working with at NIST are now where I would say astronomy was 2 decades ago. So it's taken some time, but we're chipping away at it. No pun intended.
I think astronomy, I think astronomy had the advantage of having the kind of the community norms around sharing, because they had to share instruments. I mean, you only get a single instrument. They had to come together on, this is what we purchased, we all share it, and that norm is absent in other communities. And I think that is what has given that, plus the data is useless for everyone.
Well, major observatories cost $1 billion. And there's a limited number of them. So yes, they're all shared use facilities. You're proposed to get time on them. You can't afford not to properly archive the data, and because it's just too valuable.
cooperate.
And the night sky changes. So that's what the latest ground-based telescope, the Rubin Observatory, is designed to do, is to take image essentially the entire night sky every night with different time intervals to look for variable objects. Things that are moving, things that are changing brightness, exploring the time domain at a level that's never been done before. So all the data is important over all time. It's another difference about astronomy. We want it all. We want to keep it all forever.
Anyway, thank you.
Yeah.
And Gary Motes from IU Collection says there's a ton of bio collection data sets, and he's very happy to connect you to any of those here at IU and beyond.
Super.
Yeah.
I don't know about them all, sorry.
Well, thank you all. Appreciate everybody making the trip. Here.
Like,